And now I want to ask again Christian Ramerstorfer from IAE, the Institute of Sustainable Technologies, for his contribution about the basics of flue gas cleaning. Christian, please, the stage is yours.
Thank you, Heidrun. So welcome again today to the presentation about basics of flue gas cleaning. In this part of the webinar, I would like to present some important basic technologies which are applied at biomass district heating plants for dust precipitation and reduction of nitrogen oxides in the flue gas. In the first part of the presentation, we'll refer to three important particle removal technologies, as well as flue gas condensation, which is somehow interlinked to particle removal. And then in the second part, we'll focus on reduction of nitrogen oxides in the flue gas, or DENOX, as it is called short. Yes, let's start with technologies for particle removal. A very simple technology that's used is are cyclones or multi-cyclones, which are basically centrifugal separators. You can see the principle on a sketch here on the right picture. The flue gas with the dust enters a cyclone body and is accelerated to a high-speed rotational flow within the cyclone, and then exits through a gas outlet tube in the center. Coarse fly ash particles are separated due to centrifugal forces because they cannot follow this accelerated flow, and then are separated to the walls and drop down into this conical section and are removed at the bottom by means of a rotary valve which ensures the air tightness of the system. This only works for coarse fly ash precipitation with particle diameters of more than 5 micrometers. An advantage of this technology is the wide operation window. It is possible to operate these devices to up to more than 1000 degrees Celsius, which is only limited by the temperature resistance of the material used. Usually this is designed as a multi-cyclone, as you can see on the picture here. Yeah, dust loads downstream, a multi-cyclone is in the range of about 150 milligrams per normal cubic meter. This technology is state-of-the-art for industrial biomass combustion plants and usually directly integrated into the boiler section or like here as a separate unit downstream the boiler. If there's a need for even lower dust emissions, also for the precipitation of fine dust, electrostatic precipitators are used. Here the flue gas is fed into the electrostatic precipitator, and particles that flow through the filter are negatively electrically charged at ionizing electrodes, and then move in the direction of collection plates due to electrical attraction. A wrapping mechanism you can see here with hammers is used to periodically clean the collected dust at the collecting plates and there are two possible operation modes. One is a dry operation, which is state-of-the-art for plants which have to meet dust emissions below about 50 milligrams per normal cubic meter. Another option is the operation with wet flue gas for applications downstream flue gas condensation units. Yes, but these are rarely installed in plants in practice. What has to be considered is that there is a minimum operation temperature regarding the flue gas temperature entering the electrostatic precipitator of about 120 degrees Celsius. And due to the fact that this system is operated with high electric voltage, safety measures have to be considered because the high voltage power supply is in the range of about 20 to 100 kilovolts. Here you can see the construction of such an electrostatic precipitator from Scheuch on the left side. The flue gas enters here. Then you can see the ionizing electrodes and also the wrapping mechanism for the cleaning of the collecting plates. Several of these channels with ionizing electrodes and collecting plates are in parallel here. All the housing of the ESP and the collecting plates are electrically grounded, so in principle it's safe to touch it from the outside, let's say. Only the ionizing electrodes itself carry the high electric voltage and therefore have to be well insulated from the environment. As you can see here on the top, the yellow part is the electrical insulation of the high voltage part. On the right side, you see an example of an ESP at the biomass district heating plant in Maria Gugging in Lower Austria, which is about a 4 megawatt thermal output plant. And you can get some impression about the dimensions of such a filter. A very common combination of the two technologies I just presented is a combination of a multi-cyclone and electrostatic precipitator for a first stage cleaning from coarse fly ash and then a second stage for the cleaning of fine dust. What also can be seen here are several devices for maintenance access, like ladders or platforms, also a manhole for inspection of the electrostatic precipitator during revision. And what also can be seen is the de-ashing system, and here with separated ash fractions for the multi-cyclone and the ESP, and with direct ash discharge into the containers. Yes. So even lower dust loads in the clean flue gas are possible with by the use of baghouse filters. Their fabric filters are used. The flue gas here is passing fabric filter bags from the outside to the inside, and the dust is collected on the surface of these filter bags then. With this technology, almost 100% dust removal efficiency is possible, also independent from the particle size. Dust loads of the cleaned gas are usually below 5 milligrams per normal cubic meters. About 180 degrees Celsius minimum operation temperature of the flue gas is needed here, so even a bit higher than for ESPs. And for baghouse filters, the dust removal from the filter bags is done by an impulse cleaning system. You can see on the top here. With this impulse cleaning system, there's a frequent back pulsing with compressed air done, which blows off the filter cake, which builds up on the surface again, and then the precipitated dust falls into the bottom section and again into the de-ashing system. This technology is already beyond state of the art for biomass district heating plants and only used for special purpose, for instance, for plants with waste wood combustion. Then I would like to have a short look on flue gas condensation. Primarily, this is not used as a technology for dust precipitation, but for heat recovery. With flue gas condensation, it is possible to recover sensible and latent heat. The feasibility mainly depends on the moisture content of the fuel and suitable return flow temperatures from the district heating grid. But in any case, this also has additional positive effects on dust emissions. It is recommended to install an ESP upstream, such a flue gas condensation unit, in order to reduce problems regarding corrosion of the heat exchanger, and also of issues with the composition of the condensate that is produced. So even if there is no ESP applied upstream, dust loads in the gas of less than 50 milligrams per normal cubic meters are possible due to a certain scrubbing or washing effect of the condensate. Almost 100% of the coarse fly ash is precipitated in a flue gas condensation unit. And yeah, but also should be mentioned that due to the wet operation, it is stainless steel material is needed for the heat exchanger, the condenser here, and periodic cleaning of the heat exchanger is done with processed water. You can see here. This is also giving an option to use this as a scrubber if it is operated continuously, or yeah, like a flue gas scrubber. Or, yeah. Here you can see an already rather complex system, which is installed in a plant with 5 megawatts heat output. Again, with the combination of a MULTI-CYCLONE and an ESP, and in this case also a flue gas condensation unit with several economizer heat exchangers, and then condensing stage for flue gas condensation. Yeah, as you can see, this is already there's already an increased space demand for the whole flue gas cleaning system, and of course also regarding costs, this is already getting more expensive. So at the end of the first part, I would like to give again an overview on the most important key figures regarding dust precipitation technologies. So regarding particle size with cyclones, it is possible to precipitate particles greater than about 5 micrometers. with electrostatic precipitators in the range of equal or greater than 1 micrometers. Backhouse filters can precipitate almost all particle sizes. Regarding the dust content in the cleaned gas, here we have values of in milligrams per normal cubic meters and 11% O2 in the flue gas. For cyclones in the range of 120 to 200, ESPs offer 5 to 50 milligrams per normal cubic meters in the cleaned gas, and even lower for backhouse filters with 1 to 5. Then again, the minimum and also maximum possible operation temperatures of the flue gas, as I already said here, for ESPs in the range of 120 to 130 degrees for minimum temperature, and backhouse filter a bit higher in the range of 180 to 220. Also, ESPs and backhouse filters are rather limited regarding the maximum operation temperatures to around 300 degrees Celsius. What also has to be considered regarding flue gas cleaning is the pressure loss of the system. As you can see, cyclones are in the range of about 6 to 15 millibars pressure loss, which is in any case has to be considered in any case because this is really state of the art. If we compare ESPs and backhouse filters, you can see that ESPs have a considerably lower pressure loss than backhouse filters. So this is an advantage regarding the capacity of the flue gas suction fan needed for the ESPs here. So I would like to go to the second part of the presentation now regarding the reduction of nitrogen oxides in the flue gas. At this figure you can see the nitrogen oxide emissions of biomass plants independent of the fuel nitrogen content for native wood, as it is usually used in district heating plants. We are in the range of about 200 to 300 milligrams per normal cubic meters of nitrogen oxides in the flue gas without any additional measures for conventional combustion here. With appropriate primary measures, like we heard today, air staging and appropriate control of the combustion, it is possible to get to values close to 100 or in the range of 100 milligrams per normal cubic meters. If values lower than that are needed, secondary measures have to be applied, and this is done by selective non-catalytic reduction or selective catalytic reduction, which I want to present in the following. So at first, selective non-catalytic reduction is a still rather cost-effective solution to reduce nitrogen oxides in the flue gas. This is done by injection of ammonia or urea in the secondary combustion zone. Up here, above the grate in the burnout zone, these injected reducing agents then react with the nitrogen oxides in the flue gas to elemental nitrogen. And of course, there are also byproducts like water and CO2. This technology works in a temperature range of the flue gas of 850 to 950 degrees Celsius, so rather high temperatures, which are present in a secondary combustion zone. Reduction efficiencies are possible in the range of 60 to 70%, which can then bring down the nitrogen oxide content in the flue gas to below 100 milligrams per normal cubic meter. What has to be considered is that the non-reacted ammonia is emitted. This is also referred to as ammonia slip, which is usually below 10 milligrams per normal cubic meter. And as I already said, still this is a rather cost-effective solution. If a higher reduction efficiencies are needed, there's a possibility to use selective catalytic reduction. This is similar to the nitrogen oxide reduction technology that's applied in diesel engine cars. There, the reduction of nitrogen oxides takes place with ammonia using a catalyst material in a temperature range of 170 to 450 degrees Celsius. With this technology, it's possible to achieve reduction efficiencies of 80 to 95%, so considerably lower than with SNCR. Also, the ammonia slip is usually lower in the range of 1 to 5 milligrams per normal cubic meters. But there are some issues if this technology is used in biomass plants due to catalyst deactivation, because there is a lot of potassium and other alkali compounds in the flue gas, which is harming the, or can negatively influence the catalyst material. And also what has to be considered is that the investment costs are considerably higher than for selective non-catalytic reduction. So I'm already coming to the end of my presentation. I would like to send like a concluding message again. It has to be considered that flue gas cleaning is a really important plant component. This is really important in communications with authorities regarding operating permit and so on. Also regarding public acceptance, because these are important measures to ensure air quality around the biomass district heating plant. And it requires special attention and profound planning. So please really evaluate the local legal emission limits you have. Select a suitable technology according to the emission limits, and yeah, especially consider space demands of the flue gas cleaning system in the plant, and of course also costs. So thank you very much for your attention, and yeah, feel free to ask questions, please.
Thank you, Christian, for your very interesting presentation that showed us different technologies for reducing emissions from the flue gas with different methods like filters, cyclones, catalytic and non-catalytic reduction, and also flue gas condensation, also with the very nice aspect of recovering heat and so improving the efficiency of the plants. Now, if you have questions, we have now more time. Thank you, Christian.
Welcome.
So feel free to ask your questions, please.
Christian, this is Matteo from Italy.
Hello.
Very interesting presentation. One question: is there a minimum size from the nominal power point of view to which the application of these technologies could be cost effective? Because I mean, in small plants, for small I mean less than 1 megawatt, I usually don't see the application of these technologies. What's the situation in Austria, for instance? Thanks.
Yeah, I don't know. I mean, multi-cyclones, as I said, is really state of the art, and almost all manufacturers have this in together with their boilers. The installation of an electrostatic precipitator, of course, is already causing costs that have to be looked more closely into. I mean, for plants smaller than 1 megawatts, usually in Austria, these are not installed, as far as I know. So this is already for plants in more than maybe 5 megawatts or in this range.
Usually the legal emission limits consider that so that you have higher allowance for smaller plants, so that it is not necessarily needed to install an ESB for plants in that size, Matteo. However, it depends on the local boundary conditions, as we discussed before. So it could be possible, even if you have a smaller plant, that you need an ESB. And then it, of course, is an issue with investment costs and operating costs, but usually it's not required.
Yeah, thank you. So situation is very similar to Italy as well.
Okay, are there other questions? Another remarks from your side? Harald and Christian?
Of course, I can say something else. No. So Christian made a very nice presentation about the state-of-the-art technologies we have in this field, which are applied in hundreds of plants. So there's a lot of experience, there's a lot of manufacturers. Every now and then you hear something about other technologies like ceramic filters. We had one plant in Austria, I think, which tried to test this. Water scrubbers are usually not used in that size of plants. And sometimes you hear of some other special technologies. But as long as there's no clear references and manufacturers cannot guarantee emission limits with that, I suggest to keep the fingers off it. You might run into trouble. So take care if you try to apply not state-of-the-art technology here.
Thank you, Harald.
And maybe another final message. There is technology out there, so it is possible to manage emissions for biomass district heating plants very well. Of course, it causes costs, but we see that we can have a significant impact on better air quality in the areas compared to individual heating units.
Great, thank you, Harald, for your additional inputs.